let's look at integrating improper integrals. And so this is integrating problematic functions. So there are two main problems that we're trying to avoid when we work on improper integrals. One is if one or both of the bounds of integration are at infinity. As we've seen before, if you try to plug in infinity into functions, it kind of breaks things. The second is if there's any point where the function is undefined or equals infinity. So we have these problems if one of our bounds is infinity or if somewhere in our function it goes off to infinity. So to evaluate this, we replace the problem, wherever that problem is, with a variable and then use limits to evaluate. So in other words, if we were integrating from 0 to infinity of f of x dx, we just rewrite that as the limit as b approaches infinity of the integral from 0 to b of f of x dx. Because we can use some variable b, and then we just do our limiting values at the end. And so that's the whole idea here. We're going to do two quick examples, and it should be nice and straightforward, hopefully. So, for example, if you have infinite bounds, so in this case I've got negative infinity as one of my bounds. I'm going to write this as the limit as b approaches negative infinity, and then I'm going to integrate from b to 0 of e to the x dx. So what's the integral of e to the x? It's just e to the x, nice and easy. So limit as b approaches negative infinity of e to the x integrated from b to 0. And then we plug that in and we get the limit as b approaches negative infinity of e to the 0 minus e to the b. And again, this is just evaluating integrals totally normally. And then we actually find our limit. So e to the 0 is equal to 1. E to the negative infinity is functionally 0. Remember, we can't actually plug in negative infinity. We just say the limit as b approaches infinity of e to the b is 0. So we end up with 1 minus 0, which is 1 for our final answer. So the whole idea here, again, whatever our problem was, in this case it was b, we just replaced that with, or sorry, our problem was negative infinity, we replaced that with b, and then took our limits. This next example has an undefined point. So if we have, sorry, that shouldn't be a 2, that should be an x. The square root of 1 over x dx, or 1 over the square root of x dx. The problem is we can't plug in a 0, so we're going to say the limit as b approaches 0 of the integral from b to 1 of 1 over the square root of x dx, and that will equal the limit as b approaches 0 of x to the negative 1/2, so we add 1, and that will give us x to the 1/2, so that will give us 2 times x to the 1/2 integrated from b to 1. That's just, again, if people need to see it, this is x to the negative 1/2, then use the reverse power rule. So that gives us limit as b approaches 0 of 2 times 1 to the 1/2 minus 2 times b to the 1/2, which will give us 2 minus 0, which is just 2. So just like before, wherever our bound was, we replaced it. Now, this is not something that's going to work, but if you had, let me think of a good example that we can show here. So if we had something like this, the problem is that x equals 4. So this would have to be rewritten as the integral from 3 to 4 of x plus 2 over x minus 4. So this would actually be a b. Now, let me rewrite this completely so it's cleaner. The limit as b approaches 4 of the integral from 3 to 4 x plus 2 over x minus 4 dx plus the limit as b approaches 4 of the integral from b to 7. And that is a b there, not a 4, of x plus 2 over x minus 4. So again, we had to replace the problem, which was at x equals 4. So we replaced it with a b. But because it was in the middle of our integral, we had to actually split it into the two individual ones. But the integral from 3 to b and then b to 7 is the same as just the integral from 3 to 7. But we just can't evaluate that individually. The limit may not always exist. If the limit doesn't exist, integral is indeterminate. Usually that means it's undefined, but there could be some edge cases where it's just a matter of this is a problem that can be evaluated otherwise. So it's usually does not exist. But sometimes there are some edge cases, but usually it does not exist. And so that's how we integrate problematic points, or improper integrals, as we call them.